Hello everyone. So today we are looking at magnetism. Today we are just focusing on magnetism. Um, Magnetism, where we are saying magnetism. This is the following chapter that we'll be looking at, and I'm just going to start with the general information about magnets. So we are saying we're going to start with magnets, looking at the nature of magnets, right? So here I'm just going to talk about a permanent magnet, whereby we are saying the properties of a permanent magnet. We say it has a north and a south pole, right? So these north and a south pole are at the end of the magnet. That's one thing that you have to understand. And also we are saying like poles attract, like poles repel. Like poles repel, and then unlike poles attract. Unlike poles attract, isn't it? So this speaks of when we have two or more permanent magnets like this one. So if you have a south pole here, we have a north pole here, we are going to have an attraction, a repulsion between these two magnets, isn't it? But if you have a south pole here and the north pole here, you're going to have an attraction between these two magnets, isn't it? So that's very important. That's one of the very important fundamental laws when it comes to magnetism. So one thing that I want us to also look at is also let's just take a look at the nature of the poles. What do you mean when you're talking about the magnetic poles? So the magnetic poles. So one thing that you have to understand is that if you have a permanent magnet like this, again, if you have a permanent magnet like this, so remember you have a north and a south, right? So one thing that you have to understand is that if you break this magnet into half, right? If you break it into half, such that you have two pieces. Okay, this is the correct part. So you have two pieces like this. Remember, this was the north, right? This was the south. Whenever we have a permanent magnet, it's supposed to have two poles, right? It's supposed to have two. You will never find a magnet with one pole, which means if you break this magnet into half, this automatic, since we have a north pole here, this automatically is going to be what? A south pole, and this is automatically going to be what? A north pole. So always the magnet exists with two poles. Unlike charges, we spoke about charges whereby you said we can have one positive charge, isn't it, in space, and we can also have one negative charge in space. But that doesn't apply with magnetism. With magnets, it always has to go in pairs, right? You have these two poles are always together. So whenever you have a north pole, there's supposed to be what? A south pole. So we don't have monopoles or single poles in magnets. And another thing, we can use a permanent magnet to charge, we can use a permanent magnet to magnetize other materials, other magnetic materials, right? So that's why we have different types of magnets. We have permanent magnets, we have also induced magnets. So how can you induce magnetism in magnetic materials? So there are few ways we can do that. So the first one, it's called magnetization. So we're talking about magnetization now. Magnetization, or let's just talk about inducing magnetism. Inducing magnetism, still the same thing with magnetization. So we're inducing magnetism. I think this one is better. So we're inducing magnetism. The first way to induce magnetism is through stroking. What do you mean by that? So like, let's say if you have a magnetic material, a rigid bar or an iron bar like this one, and then you have okay, let me just draw it here so that you can see the diagram properly. This is just an iron bar, right? It's a magnetic material. We're still going to talk about the different types of magnetic material. This is an iron bar. So we are saying if you have an iron bar and then you take a magnet, you take a bar magnet like this one, which has a north and a south pole, and then you start by, you move it, you stroke it around, you stroke it at the surface of the iron bar repeatedly. You start from one end, you stroke it starting from one end to the other, like from using the North Pole. You start by stroking once, you come back again, you stroke, you come back again, you stroke, you come back again, you stroke. It will be such that if you started with the North, if you stroke starting with the North Pole, which means this is going to be the North part of the iron bar, because we are inducing magnetism in the iron bar, right? So this is going to be the North Pole, and then this is going to be the South Pole. So if you continue to stroke, this iron bar will contain, then it will contain magnetic properties. It's going to be induced such that it contains magnetic properties. So let me just try to show you the demonstration of how we actually stroke and how we actually do the stroking, how we can induce magnetism using. So if I say my calculator, let's say my calculator is what? The rigid bar, right? The rigid iron bar, and this is going to be what? This stylus is going to be my magnet. So if the point of the stylus is what? Let's say if the point of the stylus is the North Pole, so we are going to stroke the iron bar like this, using one of the poles of the magnet, just stroking it like this. Then after stroking it several times, we are saying now the iron bar is going to contain magnetic properties such that if you bring it close to other magnetic materials, there's going to be an attraction or a repulsion. So that's what stroking actually is. We are inducing magnetic properties into the bar while stroking the bar with a permanent magnet. So that's what it means. I'm also going to drop a video on the description below that will show you the demonstration of how actually we stroke a magnetic material, trying to induce its magnetic properties. Like, I'm just going to drop a video, so you should check it out on the description below. So again, stroking is one way of inducing magnetism, isn't it? So we have stroking, and then the other one is actually quite simple, whereby if I have a magnet, right? I have a permanent magnet like this, north and south, right? I'm inducing magnetism. So like I have a permanent magnet like this, and then also I have maybe one magnetic material. Let me just call like a nail. I'm just going to have a nail close to the magnet, isn't it? So I'm saying the closer I bring this nail to the magnet is going to contain magnetic properties, such that if I maybe bring a paper clip right next to this nail, is going to be attracted by the nail. Why? Because it's closer to the permanent magnet. We are going to see what actually makes the magnetic material such as this nail to contain or to have attributes of the permanent magnet such that it attracts the paper clip. It's due to what we call magnetic field lines, or the magnetic field, which is the regional space around the magnet. But I'm still going to talk about magnetic fields later on in this video. So that's one other way of inducing magnetism on a magnetic material. So you just have your permanent magnet like this one, north, south, right? And then you're going to have your magnetic material right next to the magnet, isn't it? Such that if you place another magnetic material next to this, let me just call this the iron. Let me just call this a nail, right? Just an example. Such that if you bring maybe a paper clip or another magnetic material next to the nail, is going to be attracted. So now the nail is being magnetized, isn't it? So it contains magnetic properties. So another thing, so these are the major two ways that we can actually magnetize that we can use to magnetize a material such that it contains magnetic properties. Another one we can also use when it's called electromagnetism. I think you guys are aware of that, whereby we can have a solenoid, we can have a magnetic material like an iron core. We have an iron core, right? And then you have a solenoid around the iron core, and then within this solenoid we have actually currents flowing within this solenoid, such that now the core within the solenoid is going to contain what? It's going to contain it's going to have magnetic properties such that it's going to act as a magnet as long as there's a flow of current. But we're still going to talk about that. That's just another way of inducing magnetism into a magnetic material. So now let's talk about magnetic materials. So they are classified into two types. Magnetic materials are classified into two types. Magnetic materials are classified into two types. So the first one is we have soft magnetic materials, right? And then the second one, we have what we call hard magnetic materials. So with soft magnetic materials, it has certain properties. It has certain properties such that the first one, we are saying they are easily magnetized. And then also they lose their magnetism easily. So those are the major classifications. Those are the major properties, of soft magnetic materials. They are easily magnetized. They lose their magnetism easily. And then also these ones, they are actually used in motors. These ones are used in motors. I'm still going to talk about an electric motor. They are used in motors, transformers, generators, and all of those things, in generators, etc. etc. So they are actually used in these electrical machines to do certain functions that we're still going to look at. And then we have hard magnetic materials. These ones, they also have certain properties, whereby we are saying with hard magnetic materials, they are difficult. One thing, they are difficult. Remember, these ones are easily magnetized. This one, they're difficult to magnetize. If they're difficult to magnetize, which means they tend towards these ones, they retain, or they don't lose their magnetism easily. Isn't it? Yes, which means they can retain their magnetic properties longer than the soft magnetic materials. So those are the major things that you have to take into account when you're looking at these two different, depending on the type of magnet that you want to create. You can either use a soft or a hard magnet, but most of the time, if you want to create a permanent magnet, of course they use hard magnetic materials to create a permanent magnet, because it can retain its magnetic properties, as much as it's not hard to as much as it's difficult to magnetize, but still it can withstand, it can retain its magnetic properties longer than the soft magnetic materials. So that's one thing. So now let's get into what really magnetism is all about. So now we are looking at the magnetic fields. We're looking at magnetic fields. So we are saying with the magnetic field, this is a region of space around a permanent magnet where the magnetic force can be felt. So that's one thing that is very key. This is a permanent. We are saying this is a region of space, remember, around the magnet or around the permanent magnets where, not necessarily permanent magnet, around any magnet where a magnetic force can be felt. Because even with an induced magnet, we still have a magnetic field, right? And the magnetic field is due to what? It's due to the poles. It's due to the poles here on the magnet, isn't it? On the magnet. So that's one thing that is very key. So if you have your magnet like this, again, you have the north and the south pole. These are the properties of a magnetic field. We're saying they always move from the north to the south pole. That's one thing. They always move from the north to the south pole, and they surround the magnet. So that's very key. They surround the magnet. So we are going to have, so they move from north to south. They move from north to south. One thing that I want you guys to take from this one, so since they move from north to south, of course we have to show their direction. We have to show their direction is that they're moving from north to south, isn't it? We are showing that they are moving from north to south. And another thing, you see where they begin from the north, right? The lines, they don't touch each other here. They are separate, which means there's a point of repulsion at both the poles. There's a point of repulsion between the magnetic field lines, right? These are magnetic field lines, so they don't touch. Same thing as we discussed when we're looking at the electric charges. They don't at the surface of the charge. When they radiate, if it's a positive charge, they don't touch. Even here, you can have your magnetic field lines touching very close together. No, they can't be close, but they don't touch. Which means if I can just zoom this out, saying this is my north pole like this. So they will radiate like this. They won't touch. They don't touch. They just radiate, and they space in between them. That's very important, especially if they say draw the magnetic field lines around the magnet. So this is our north pole. Even if this is our south pole, it's still the same thing. Make sure that they don't touch here, because there's repulsion between the magnetic field lines. So that's one thing that is very important. So we are saying with the magnetic field lines, so we are saying magnetic field, of course, if we have magnetic field lines, that means there's also what? If you have magnetic field lines, there's also what you call magnetic field intensity or magnetic field strength. So remember, with electric field, we talk about electric field intensity, right? Here we also have magnetic field intensity, which is represented using, B. It represents using B, and the arrow on top of B that shows that this is a vector quantity. This is a vector quantity, so that's very important. So each and every magnet has a magnetic field around it, right? And that magnetic field actually depicts or tells us about like the magnetic field intensity of that magnet. And then one thing that you have to take into account is that if you have a magnet north south, right, we are saying at the poles there, the magnetic field intensity is going to be stronger. It's going to be stronger at the poles. B is going to be stronger at the poles. So that's one thing that you have to understand. Like the magnetic field intensity is strong at the poles, and of course it's a little bit weaker around the magnet. So that's one thing that you guys have to like take from that. And then also we while we're still talking about the magnetic field, there are different sources of magnetic fields. There are different sources of magnetic fields, and of course, the first one that we spoke about, the permanent magnet, right? We spoke about the permanent magnet, and then also we have what we call moving charges. Moving charges can produce magnetic fields. Moving charges. But before I talk about how moving charges produce magnetic fields, or how they can induce, how they can induce magnetic fields around a conducting wire, just first look at how two magnets actually interact in terms of attraction and repulsion, and how we can actually draw the magnetic field lines around those two interactions. So if we have two permanent magnets, for example, there can be two or more, but most of the time we just use two for simple illustrations. So this is the south and this is the north pole, right? We have the south and the north pole, and then we have another magnet. This one is a little bit too close, sorry. Let's say this is my north pole, and then this is my south pole. So you have two magnets, right? We have two magnets. I'm just showing these poles that are close to each other. Of course, here we have the south pole. Of course, here we have the north pole. But I just want to work on these ones. So this one is also automatically from this one we're getting what? There's going to be an attraction between these two magnetism, because these are unlike poles, right? So there's going to be an attraction. So how do you draw that? So of course we are going to have an attraction between these two magnets, isn't it? And then also we are going to have, right? And then here we are having, they are coming into the magnet, right? So of course the lines don't touch, isn't it? The lines don't touch, and then you show the direction, right? It's always from north to south. It's always from north to south. It's always from north to south. From north to south. So this is how this is just one standard way of representing of how you can draw the interaction between two magnets, right? So these three lines in the middle, they show the attraction between the two magnets, because these are unlike poles, which means there's attraction. So how do you represent then two magnets with the same polarity? Two magnets with the same polarity. So now we can have north, or we can have south, it doesn't matter. So if you have north, of course there's going to be repulsion, which means you can draw magnetic field lines like this, right? And also the same way this side, they don't touch. So this is repulsion, right? There's nothing in between these two poles, right? So of course you draw it's always from north to south. From north to south, you represent that. From north to south like this, right? On both cases, it's from north to south. Make sure that you always draw the arrows, because they show the direction of the magnetic field lines. So this is how you can draw the magnetic field lines between two magnets with the same polarity. And then also we have, if you have south, still the same thing. Just bring them closer. If you have south poles, right? So same thing, there's going to be a repulsion between these two. Make sure that your lines don't touch. And then since it's south, the arrows are going to come in, because it's always from, and this side is north, right? So they are moving like this. So even the south is north, so they are moving like this. So they are coming into the South Pole. They're coming into the South Pole. So this is how you can basically represent. This is the interaction between two magnets when you have when they're close to each other, when their ends are close to each other. When you have the same polarity, and when also have a different polarity. So now let's talk about we said there are actually two ways in which we can induce magnetic field lines, right? The first one we just spoke about, we have a permanent magnet. So now let's talk about moving charges around a conductor. So this is very important. This is a very key insight that you guys have to really pay attention on, because because later on I think we're going to talk about Faraday's laws, and also Lenz's law. So these are actually depicted from this concept, and then they're very important because actually with electric motors and all of those things, they use these conductors. They use these principles. So let's talk about. We're going to talk about. We are going to talk about the magnetic field lines around a current carrying conductor, right? Magnetic lines around a current carrying conductor. Magnetic field lines. Magnetic field around a current carrying conductor. Current carrying conductor. This is very important. So this concept is very key. So one thing that I want you guys to do. Let's imagine. We are just going to imagine. This is our wire. Current carrying conducting wire, right? Of course, the end is connected to. Of course, this wire is connected to what? Is connected to a power source. It's connected to a power source. But we are looking at this part. Of course, there's moving charge, isn't it? There's moving charge. Say this is the negative. Let me say this is positive. This is negative. So we have current moving in this direction within this wire. Right? We have current moving in this direction. So which means if current is moving in this direction, which means even the positive charges are moving in the same direction, right? So we have positive charges moving in the same direction within the conductor. So what happens? We are saying if we have charges or positive charges moving in the same direction as the current, right? When we looked at electrical charges, this is what you said. So if we have our currents moving in this direction, we are going to have magnetic field lines forming around our wire. So of course these are many field lines that are forming around the wire. So we are saying, then how do you, it's like if I can make an example, if you have a long wire, right, they're just whooping around the wire. You have magnetic field lines whooping around the wire. So how do you determine then? Just try to imagine this structure in a 3D form. Try to imagine it in a 3D form. You have these magnetic field lines in a circular motion, or in a circular, that just circles around the wire, right? This wire is just standing straight, and then you have the magnetic field lines around it. So, and then how do you determine the direction of these magnetic field lines, right? So how do you determine the direction of these magnetic field lines? We use what you call the right-hand grip rule. Use the right-hand grip rule. So so basically, what do you have? You have your right hand, right? You have your right hand. So this is the grip rule, whereby if you go to your conductor, you pretend as if you are gripping your conductor like this, right? So with your right hand though, so which means your thumb represent the direction of the current, and then the other fingers, they will represent the direction of what? The direction of of the magnetic field lines around the current carrying conductor, isn't it? So if I'm just gripping this wire like this, which means this is the direction of what? Of my magnetic field lines. So I'm going to have the direction of my magnetic field lines like this. They're going to be in this direction, in this direction. They're going to be in this direction. So it's like I'm gripping onto the wire. So, but also I'm going to drop a link for a video that is actually going to explain how the right hand grip rule actually works in this case. So this is a very important rules that you guys have to understand. The right hand grip rule, we're still going to mention about the left hand, Fleming's left hand rule, Fleming's right hand rule, all of those. So this is how you can actually detect the direction of the magnetic field lines around what? Around the current carrying conductor, right? So just to state that again, because it's very important, this is our wire, right? This is our wire. It's carrying a conductor. It's carrying a current of I, right, in this direction, which means we're going to have our magnetic field lines moving like this, isn't it? They are moving like this around the current because due to the right hand grip rule. So that's very important. And we use it for most calculations, because remember we said the magnetic field intensity, which is with the magnetic field intensity, which is due to the magnetic field line, is a vector quantity. We represent it with B, right? With B with an arrow to show that is a vector quantity, right? So we need to know the direction. It's very important that we know the direction. So remember when I mentioned about inducing, if we have a bar magnet like this one, and then we said we are going to induce the properties of a magnet within this nail. We said when you bring this nail closer to the magnet, it's going to have magnetic properties. But what remains is why does it then attain a magnetic property? So remember, you have your magnetic field lines, right? You have magnetic field lines. If the nail is within these magnetic field lines, then it's going to have magnetic properties. So that's why you have to bring it closer to the magnet such that it's within this region, right? The region whereby you can have your magnetic field lines of the permanent magnet, so that the nail can then attain what? The magnetic attributes. So now let's move to, we have spoken about how we can induce magnetic field around a current carrying conductor, right? So let's move on to the Earth's magnetic field. The Earth's magnetic field. The Earth's magnetic field. So same with the permanent conductor, permanent magnet. We still have the same thing. We are saying at the North Pole of the Earth we have. Remember, when you did geography, we said the Earth is flattens at the poles, right, and bulges at the equator. So this is sort of like this is the North and the South Pole, right? This is the North and the South Pole. So if this is our Earth, which means we are going to have the magnetic field lines moving in this direction. The magnetic field lines moving in this direction, right? They'll be moving in this direction. So we are going to have them moving from the North to the South Pole, from the North to the South Pole, from the North to the South Pole, right? You can use a compass to determine the direction of the, because always the compass will point from north, right? The compass always points towards the north. So we can use a compass to find the direction of the magnetic field line within around the Earth, right? So another thing that I want you guys to understand is that with this one we are saying the source of the Earth's magnetic field line is believed to be sort of like the electrical current within the liquid part of the core, within the magma which is the center of the Earth, right? So like there's sort of like an electric current within the magma that actually produces the Earth's magnetic field lines. And then also the direction of the Earth's magnetic field line always changes, but over a very long period of time, like millions or billions of years, it always changes the direction of the magnetic field lines. So now let's actually look at the, we want to look at the, if remember, we said within a moving charge, within a moving charge within a conductor is going to have what? Magnetic fields, right? So now we want to look at the force within that conductor. So we are saying, if you have your conductor, your wire like this, a conducting wire like this, if there's a moving current, I, right? So we are going to have magnetic field lines around the wire. So within these magnetic field lines, within a magnetic field, remember when I gave the definition for magnetic field, I said the magnetic field, and I said this is the region of space around the magnet where the magnetic force can be felt. So how can you find the magnitude of the magnetic force? How can you find the magnitude of the magnetic force around the current carrying conductor? So there are things that you have to know for us to find the magnetic force around the current carrying conductor. So first of all, we are saying this was done due to experiments whereby they discovered that the force within a current carrying conductor, first of all, is directly proportional. It's directly proportional to what? To the current within the conductor, which means it's also directly proportional to the charge, the number of charges moving in that conductor, and it's also directly proportional to the length of the conductor, right? So those are the two major things that you have to understand, that the force, if you increase these two, the force is going to increase. If you decrease these two, the force is going to decrease. So the force, the magnetic force, let me just call it Fm, the magnetic force around this current conductor is directly proportional to the current and the length of the wire, right? And then also, let's say so we are saying now we are saying F is directly proportional to I and L, right? F is directly proportional to I and L. And then now we're going to have since these two are proportional, so if we want to create an equation, we're going to have the constant of proportionality, and then our constant of proportionality is going to be the magnetic field intensity. Our constant of proportionality is going to be B, and then we know that B is what? B is the magnetic field intensity. Our magnetic field strength or magnetic field intensity is the same thing. Intensity. Our magnetic field intensity, right? So this is very important. This formula is very important. It is very key. So, but now, what if we have? We also use it in different scenarios. So, like now, what if you have your wire, right? You have your wire, like which is tilted, isn't it? So you have your wire that is tilted. You have your magnetic field lines. Your magnetic field lines in this direction, right? You have your I current moving in this direction. So now your wire sort of makes an angle theta, isn't it? It makes an angle theta with what? It makes an angle theta with the wire, isn't it? Your wire makes an angle theta with the magnetic field lines, right? So we are saying now we can rewrite this formula F B I L. We can add this term sine theta, what does this mean? This means that in order for you to get the maximum force, we are saying the charges, or we are saying the current moving in the conductor should be perpendicular to what? To the magnetic field lines. That's very important. In order for you to get the maximum force, you have this current or the charges within the wire moving perpendicular to what? To the field lines. These are your field lines. These are your field lines. These are your magnetic field lines, right? So that's one key thing that you guys have to take note from. So which means now we can rewrite this formula in terms of charges and just velocity, because we want to know the relationship between the force, the magnetic force around the wire, with how does it relate with the charges themselves and also their speed. So how do you derive that one? So hopefully you have to memorize the formula, you have to know this formula, you have to know where it comes from, right? Just as I derived. So now let's look at the nature of this formula again. So if we have F is equals to the magnetic field intensity times the current times the length of the wire sine theta. Remember we said if the current, if the charge is flowing through the wire are at the right angles to the magnetic field lines, we are saying you're going to get a maximum force, right? Which means theta is what? Theta is 90, right? Because we are saying B has to be at the right angles to what? To I, isn't it, right? So the magnetic field lines has to be at right angles to what? To the charges moving within the wire. So our theta is going to be 90. But if our theta is equals to 0, what does this mean? This means that if our theta is equals to 0, which means sine 0 is what is 0, which means our force is what? Our force is equals to 0. This can only happen only if the charges within the conductor, they are parallel to the magnetic field lines. If they are moving alongside with the magnetic field lines, then we're not going to have any force acting on that wire, right? So now let's represent this formula in terms of the charges themselves and the drift velocity of the charges. So based on this formula, we have the magnetic field intensity, we have the current, right, within the wire, we have the length of the wire, and then sine theta. So now remember we said charge is equal, when you're looking at this circuit, we said charge is equals to IT, right? Which means I is equals to, I'm just going to use the small letter Q. I is equals to Q over T, right? Still the same thing. I just made I the subject of the formula. So instead of I here, let me substitute Q over T, right? So I'm going to have F is equals to B. Instead of I have Q over T. Q, of course, is the charge, represent the charge, right? And then Q over T times L sine theta, right? So this is where we are with our derivation. So now I want to rearrange this formula, whereby now I have F is equals to what? Is equals to B Q L over T sine theta. So what I want you guys to understand is the drift velocity. We know that velocity is what? It's distance over time. So now our distance is going to be the length of the wire, and then also over the time. So if you know the time it took the charges to move along the length of the wire, we can find the drift velocity of the charges. So therefore, with this, now we can say our F, the force, the magnetic force within the wire is equals to what? Is equals to the magnetic field intensity times Q times V, which is the drift velocity Vd, sine what? Sine theta. So this formula is very important. This formula is very important. So we have the magnetic force around the wire, we have the magnetic field intensity, then this is the charge, then the drift velocity of the charge, sine theta. So this is very important. I want you guys to pay attention to that. So this is the formula that we use to find to actually find the magnetic force around the wire. And then I want you guys to look at something. So what are the units of the magnetic field intensity? Of course we can make F is equals to B QV sine theta, right? So our magnetic field intensity is going to be equal to what? F over QV sine theta, isn't it? which means it's directly proportional to what? It's directly proportional to F, and it's also inversely proportional to the charge, to the product of the charge and the change velocity. And then we measure the unit of the magnetic field intensity. It's Tesla. It's Tesla, and the symbol is capital letter T. We use capital letter T to represent Tesla. And if we want to find the SI unit for Tesla, we know that force is what? Force is newtons, right? We know that force is newtons over charge is what? Charge is coulombs. Velocity is what? Velocity is meters per second, isn't it? Meters per second. And then we know from this one, it's meters per second, which means we have Newton over Coulomb times meters per second. And then from this one, we can actually see that Coulomb per second times meter, right? Coulomb per second is what? Coulomb per second is current, because remember current I is equals to charge over T, right? So Coulomb per second, this is what we have. So we can represent them as Newton amp per meter. Of course, we can also break Newton, because Newton is a derived unit. We can also break Newton in terms of mass and acceleration. But let's just leave it to this form, right? We can also break if we want the SI unit, which means with kg meters per kg meters per square second, right? Over the amps times meter. So of course the meters are going to divide each other, which means 1 Tesla, 1T is equals to kg a to the power negative 1 s to the power negative 2. So this is 1 Tesla. Just in case if they ask you to derive the unit of Tesla to the SI base unit, so this is what we get. So coming back to our formula, we are saying we have the magnetic field intensity, which is represented as F is equals to QV sine theta, right? We measure this using Tesla, the symbol T. So you need to know the unit. And then we also say we can also change the unit for Tesla into gas, which is G, whereby we are saying 1 Tesla is equivalent to 1 times 10 to the power 4 gas, where G is the symbol for gas. Depending on the question, they might say you have to convert it can depend on the question whether you can represent it in Tesla or in gas. Either way, it doesn't matter. So we spoke about the right hand grip rule, whereby we wanted to see the direction of the magnetic field lines around a current conductor. So now there's this very important concept that you guys have to get. So if we have a charge, right? I have my charge Q, a positive charge, and then I have also external. This is just a single charge which is exposed to an external magnetic field. It's exposed to an external magnetic field, right? So these arrows, these sides, they represent the charge moving into the plane. They're just moving into the plane. Remember, if it's a dot, which means they move outside of the plane, they're moving out. But since I have these crosses, which means they're moving into the plane, right? And then these are the magnetic field. They represent the magnetic field. This entire region is magnetic field. This is the magnetic field region. So now we want to see what is going to be the motion of this charge when it's exposed to external magnetic field, right? So what is going to be the nature? How is it going to move? So one thing that you guys have to understand here, of course, there's going to be a magnetic force acting on this charge, right? Because it's within the magnetic field. Of course, there's going to be magnetic force. And this charge is going to move again with a velocity, right? It's going to move with a velocity. So now what I want you guys to understand is that, let me redraw this. Let me just redraw this. We have your Q, your positive charge, right? Within the field, within the magnetic field, So now we are saying if your charge is within a magnetic field, an external magnetic field, one thing that you guys have to understand is that the charge is going to move in a circular motion. Your charge is going to move in a circular motion. The charge is going to move in a circular motion, due to the magnetic force. This is due to the magnetic force. This is due to the magnetic force. That's very important. So now your charge is moving in a circular motion due to the magnetic force. And then we are saying, one thing that you have to understand is that as it's moving, we are saying the velocity, first of all, the velocity that the charge would be moving with, which is the velocity v. The velocity is going to be normal or perpendicular to the field. So we are saying our fields are moving into the plane, isn't it? So they are going to be at right angles towards, they are going to be at right angles to the just velocity, the v, just velocity of the charge. That's one thing that is important. And also we are saying the force acting on this charge is going to be, towards the center, right? Just that if the charge is moving in this direction, such that if the charge is here right now, it's moving with a velocity v, this is the charge, right? The force is going to point in there towards the center, right? This is the magnetic force, Fm. This is the magnetic force. So now we have this charge moving due to the magnetic field, right? It's exposed to the external magnetic field. It's going to move in a circular motion. While it's moving in a circular motion, always the velocity is at right angles to the magnetic field. And then we are saying the force is moving. The force is always towards a center, right? It's always towards a center. So what does this mean really? So now there are two things that you guys have to understand about this. Is that now the magnetic force will cause this charge to move with what we call a centripetal acceleration. I think last semester we talked about centripetal forces, but if we didn't, it's fine. It's going to move with what we call a centripetal acceleration, which means the direction of the velocity is changing, of course, right? But it's always perpendicular towards. It's always perpendicular to the magnetic field lines, right? So now, if you have a body that is moving in a circular motion, right? You have your charge, so your charge is going to move in a circular motion. This is your charge, right? This is your positive charge is moving in a circular motion. We are saying the velocity, one thing that you have to understand with the velocity is going to be tangential to the velocity is tangential to the path of the charge, right? And also this velocity, your v, is what is perpendicular to? It's perpendicular to the magnetic field. And then also we have a force that is directed toward the center of the path, right? Toward the center of the circular path. And this is your magnetic force, right? So this magnetic force that is pointing toward the center produces what we call as a centripetal acceleration. So a centripetal acceleration is what? A represents the centripetal acceleration is equals to v squared over r. And then what is r? R is the radius. R is going to be the radius of the path, because remember this is a circular path, right? So of course we have a radius. R is going to be the radius of the path, and then v, of course, this v is just the velocity that is the velocity that these charges are moving with along the circular path. So this is the formula that we use to calculate our centripetal acceleration. This is our centripetal acceleration. Centripetal acceleration. Centripetal acceleration. So this is very important. This is a very key concept. So now if we know our centripetal acceleration, using Newton's second law of motion, we know that F is equals to ma, right? So now we know the value of a, so which means our centripetal force now, because the centripetal acceleration is going to cause the centripetal force, and our centripetal force in this case is going to be the magnetic force that is pointing toward the center, because whenever we have a circular motion due to a certain force, the force always has to point towards the center of that circular motion. So now our centripetal force, which is the same thing as the magnetic force due to these external field lines, is going to be what's going to be m, which is the mass of the charge, times v squared over r. So this force is very important now. So now we have our magnetic force. We can represent it as mv, right, as mv squared over r, isn't it? So this is how we can represent our magnetic force, right, which is causing our charge to move in a circular path around the external magnetic field lines. So now remember again, we represented the magnetic force as what? We represented magnetic force as F is equals to the magnetic field intensity, which is our B, times what? Times Q, times what? Times V sine theta, right? But in our case, let's just ignore the sine theta. Why? Because we said the velocity is what's perpendicular to the magnetic field lines, which means our theta is what? Which means our theta is 90, and then sine 90 is what? It's just 1. So we are going to ignore that, which means we're going to have F is equals to PQV, right? So I want you now, these have the same magnitude, because even this is the magnetic force, this is the magnetic force, so they have the same magnitude. So now let's look at, we can find the relationship between these two equations. So now we're saying the magnetic force due to the centripetal acceleration is what? It's mv squared over r is equals to the magnetic force, isn't it? Is equals to b times q times v, right? So now what I want you guys to understand from this equation, of course we can simplify this equation whereby we have our velocity dividing each other, and then we can make r the subject of the formula, which means the radius of the circular path is going to be equals to mv over bq. So now when you pay close attention to this equation, this equation is very important. Why is this equation very important? Because this equation is called the cyclotron equation. We call this the cyclotron equation. This is called the cyclotron equation. And it's very important. It's called the cyclotron equation. And then why is it important? Because from this equation, we can see that the radius of the circular path is directly proportional to the momentum of what? The momentum of the charge, right? Because remember, we said momentum is what? Momentum is equal to mass times velocity. So our numerator here is what? Is the momentum. So we know now that the radius is directly proportional to the momentum of our charge, isn't it? And also is inversely proportional to the magnetic field intensity. So those are the major things that you have to understand about this equation. So this is the one equation that you have to remember again. They can want you to make any. So now from this equation also, you can get, let me just, R is equals to the momentum mv, right? Divided by the product of the magnetic field intensity with the charge, right? So now we can also find the magnetic field intensity using this equation, which is going to be what? mv over rq. So now you should pay attention to the questions that you're asked, because remember, you can also find the magnetic field intensity P is equals to F over what? F over QV sine theta. So it depends on the type of question, depends on the scenario, like when you're reading a question. So now you have to know this equation, you have to know their meaning behind, right? So which means also the magnetic field intensity is directly proportional to the momentum of the moving charge. That is very important. But then now we said for this equation, for us to apply this equation, we said the velocity of the moving charge is supposed to be perpendicular to the magnetic field lines, right? What if it's not perpendicular though? What happens? We are saying then our charge, this is no longer, our charge won't move in a circular motion if V is not perpendicular to B. We are saying then our charge will move, the charge will move in a spiral. The charge is going to move in a spiral, and then it's going to move in a helical path, a helix. Like if you know a helix, for those of you that about DNA, the helix structure of a DNA, it's going to move in a helix, right? It's no longer going to move in a circular path. It's just going to move in a helix. Right? So that's one thing. If it's not perpendicular, if the V is not perpendicular to the magnetic field lines, it's going to move in a helix. And that's in a continuous helix also. It's just going to move continually, right? So these are the major key concepts that you have to understand about magnetism. But beside that, with the next video, I'm going to touch on the current, I'm going to touch on the torque. Okay, let me just talk about the torque on a current carrying conductor, and then with the next video we're going to look at electric motors and so forth. So with the torque of the remember we said a torque of a current carrying conductor. We spoke about the torque. We said a torque is what? A torque is the force times the perpendicular distance between two forces, right? That's at right angles to each other and they have the same magnitude. If you apply a force on this rod, and then there's also a force on this rod, they are opposites to each other, and they have the same magnitude, right? They have the same magnitude, and they're separated by distance d between each other. So the torque of this system is going to be what? T is going to be what? T is going to be Ft, right? And this is the center, isn't it? So that's how you can find the torque of this system. But since in this scenario we have already used T, because we said T is the unit for magnetic field intensity. Let's use tau, which is going to represent what? Our torque, which means we're going to use tau is going to be Ft in this case. Let's use tau as Ft in this case. Tau is a Greek letter. Tau is a Greek letter that we're going to use now to represent the torque of our system. So now the same thing, if you have a current carrying conductor, and then now you have external field that are acting on that current carrying conductor, you have your current carrying conductor like this, right? It has the length, you know the length of this. This is the length L. This is the length of the current carrying conductor that is exposed to magnetic field lines, right? That is exposed to magnetic field lines, isn't it? And then of course you're going to have the magnetic force acting on this current carrying conductor with the magnitude F. Because since we have since we sort of like have the same uniform magnetic field acting in this region of the current carrying conductor, the force is going to be in there. It's because the magnitude of the force is going to be the same, right? Such that if we know this as the center, right? Which means this is L over 2. This is L over 2, which means half of what the total length of the of the wire, right? This region from here to here is half of the total length. From here to here is half of the total length, because we know that the total length is L, right? So still here we can say our torque is what? We can say the torque due to the current conductor is going to be what? F T, isn't it, right? Our force and the perpendicular distance between these two forces, which is L. But remember, we said our force is what? Our magnetic force is going to be B I L, isn't it? This is what we did. So now if we substitute here tau, which is the torque, we're going to have magnetic field intensity, the current times L times what? Times D. Oh, sorry, times L, isn't it? Sorry, our FD, right? And D here, D in our case is the same thing as L, isn't it? So we are going to have our F is going to be B, which is the magnetic force intensity, times current times L, right? Times the L here. Let me just rewrite this as tau is equals to FL, isn't it? Which is the same thing as T. So our F, this is our F now, this is our L. L times L is what? Is L squared, which means from here we get that our tau is equals to our tau is equals to B I, going to have B I, isn't it? L squared. And then we know that the area is what? Is L squared, which means now we can say that the torque around the current conductor is going to be the magnetic field intensity times the current times the area of the wire. So this is how we can actually find the area of the wire. But then this area, let me just talk about this A. So I use the single wire, but normally if you have a loop, this is your current conductor, like this is exposed, is exposed within magnetic field lines, isn't it? This is just a sort of like a loop of a current conductor. This length is going to be let's represent this length as L, and then this length is B. Yeah, if I can just use those symbols, A and B, L and B, sorry, I'm using L and B. And then now we are saying we are going to have of course the force acting on this wire, right? We're going to have the force acting on this wire. So now our torque, remember we've derived the formula for our torque is equals to B I A, right? So if you have a loop like this one, a loop of a current conductor, so now our A here is going to be what? L times B. Our A, if only you have a loop like this one though, it's going to be our L times B. So this is going to be the area of this loop if you want to find the torque. So you should pay attention to that. So this is what we have done today. The other video is I'm going to talk about electric motors, and then also I'm going to talk about Am's law and all of those. And then yeah, we're still going to do a lot of concepts. So yeah.